Hi everybody, welcome back to another 102CD 102CM video. So today we're going to be looking at complex notation and basic RLC circuits. So circuits comprising of a resistor, an inductor and a capacitor. So let's get into this, shall we? So all this comes from chapter 13 of the course textbook. Some of you will probably have done complex numbers maybe at A level as part of your mathematics modules. So some of this might be revision for you. So we're going to talk about complex numbers, the complex conjugate, complex impedance, and then talk about resistance, inductance and capacitance in a context of an AC circuit. And then that will lead us into topic number 11, where we look at a circuit which has all three of them put together. So as we said in our last video, we have our axes. So our x-axis is our real number and our y-axis is our imaginary number. So the rectangular form uses for complex number notation, and the angle vector is to be taken as the hypotenuse of a right angled triangle to describe the length. But rather than describing vectors as length and direction at the moment, we're going to note them by using these complex number forms. So for example here, we've got a complex number of 2 minus j2. Notice I'm using the j terminology here. As I said in the last video, you could also, mathematicians use the terminology I, but since I is current for us, that's why we use the term j. So, and as you can see, I put both forms here for you to have a look at. So here, this vector here has a I value of 4 on the imaginary axis and an I value of 4 on the real axis. So when you write that, that'll be 4 plus I4, or 4 plus J4. And similarly, this one here has a value of about -2 or -2-ish, minus 1.5 on the real axis, and about, again, minus about 1.8 on the imaginary axis. That'll be 1.8 minus I of 1.8. So hopefully that gets that idea across to you. Yeah, this is just emphasizing what I've said. So it's I in mathematics or J in electronics. Like I said, if you're using a mathematics-based package like MATLAB or Wolfram Alpha, you would have to include the I in that. Don't use J because it won't work. That's just some other examples that you can have a look at. So why do we need complex numbers? Basically, it's to calculate the square root of -1. So if I get a calculator and I type in the square root of -1, so let me type it in now. So square root of -1, you can see there that you get an error message. Okay, so you can't do that. Okay, on a calculator. So when you do that, if you want to calculate the square root of -1, you have to use an imaginary number because it doesn't really exist. So the square of an imaginary number, so I squared or j squared, is equal to the value of -1. Okay, so if you multiply two complex numbers together and you get an answer, that answer will be -1, and then you can use that to convert that into a real number, and we'll do that in tutorial number 7 when we do some practice about complex numbers for you to have a go at. So how do you add complex numbers? So basically you just add the real parts together and add the imaginary parts together. So there's the 2 and the 2 there, and there's a j3 plus a minus j4. So you just add those together and get your answer. It's that simple. So it's just adding the real parts together and adding the complex parts together. To subtract complex numbers, we just subtract the real part, then subtract the imaginary part, similar to what we talked about in the previous slide. So here we have an example. We've got 2 plus j3 minus 2 minus j4. So we just subtract the real part. So 2 minus 2 is 0, as we said here, and j3 minus j4. So 2 minuses make a plus. So that's why we give a plus here. So we have 7j as our final answer. There's some exercises to have a look at. So exercise 1, we want to add and subtract the relative complex numbers together. So I'll go through that in the lecture. Multiplication is a little bit different, okay? So basically here we multiply the real part by the imaginary part. And an example here is if we times in A times B. So here we have 4 distinct terms. And my old mathematics teacher taught us me a way to do this, and it stuck with me for many years, even now, and she used to call it the monkey face method. Okay, so I'll show you what that means now. Okay, so I've just gone into Paint here, just to show you this a bit easier. So, say, here in Paint, I've got an A plus, plus IB, and I want to multiply that by a C plus ID term. Okay, just make that a little bit bigger. So, correction, make it a very lot bigger. Okay, so that is our method. So if I go to the pencil, then this is the monkey face method. So I multiply that term with that term, that term with that term, this term with this term, and this term with this term. So you can see this is like its eyebrows, and this is a nice smiley face. So it's smiling at you, going, yeah, we like maths. So you multiply those two terms together, so that will give you a real component. When you multiply this term together, essentially you'll get a I squared term that you can then turn into a real number. So depending on the signs that you have, that could either be a positive or negative real number. In this case, it would be negative since both of these terms are positive. You times that one there, which would give you another complex number, and this one here would again give you another complex number as well. So quite simple, nice, easy method to learn. So here's our example that we had earlier. So we've got, if we do our monkey face method, we times in the 2 by the 5, the J3 by the minus J4 term, which is over here, the J3 by the 5, which is this term here, and the 2 by the J4 term, which is here. So you've got the 4 terms, so essentially you can add those together. So you've got 2 times 5, which gives you this 10 term here. You've got the J squared term for the 3 times the 4, so you've got this minus J of 12 term here. You've got the 2 times the minus 4J, which gives you this minus J8 term here, and the 3 times the 5, which gives you the plus 15J term here. So note our minus J squared becomes a minus 1, but that minus sign is still there because the J squared becomes minus 1. So there we have minus 1, which becomes plus 1. We can add these two complex numbers together. So minus 8 plus 15 gives us a plus 7. And then we can times the 12 by the 1 to give us a real number of 12. So we add the 10 to the 12, which gives us 22 plus J of 7. Okay, so it might take a bit of practice if you're not familiar with it, but there is also the mathematics textbook that you can have a look at. One particularly good book I would recommend is Krauss, Engineering Mathematics. Okay, this is what the 5th edition looks like. This is the version I used when I was a student, so there's probably a later version out now, but still, it's a very good book, and there's a section all about complex numbers in here, because that's when I did this when I was an undergrad as well. So a very good book to have. There's another example. So you can see you multiply them out, you've got the 4 terms, and then you can collect your complex numbers, look at the I squared term to see if it becomes a positive or negative real number, just add everything together, and you get that. But notice as well, here, that's a plus, that's a minus. So this is also what's called the complex conjugate of a complex number. So complex conjugate of an imaginary number, of a complex number for that matter, is where you change the sign of the imaginary part. So if your number is 2 plus J to the 3, then you just change the sign, so it becomes 2 to the minus J3. And the interesting thing is, if you multiply a number, a complex number, by its complex conjugate, you get you just get a real number here. So essentially, you just square the real part and square the imaginary part, and that gives you, in this case, a value of 13. So you've got 2 squared plus 2 squared, which is 4, 3 squared, which is 9, so 9, 10, 11, 12, 13. Bang, bingo, there's your answer. So this is an important slide to remember. Okay, I've not got a tab on it because it's not actually got the complex conjugate message in it, but I'm just mentioning it to you now so that you know this going forward. There's an exercise where you can do some more multiplication, and we'll go through that in the lecture as well. So this is what I was saying about complex conjugate. So I'm multiplying two imaginary numbers of the opposite sign produces a real number and is equal to the square of this number. So this is one of the best tricks and is used every time to divide the complex impedance, voltage or current. So you need to know how the complex conjugate works in order to do division. Okay. Without division, obviously you won't be able to do much mathematics with it. So you have to do it this way. So if I have an A, which is 2 minus J2, its complex conjugate is 2 plus J2. And as you can see here, it's represented by an A with an asterisk on it to show you that that is the complex conjugate. So if we have this here, which is B, which is 3 plus J to the 4, then we have B star of our complex conjugate, which is equal to 3 minus J4. Okay, so you just change the sign. And as I said, this is a very important thing because you won't be able to do much of this maths without knowing this. So here's another simple exercise. So just finding the product of the complex numbers and what is the complex conjugate. Okay. I don't know why my Outlook keeps coming up as out of date. I don't know why. It's not even switched on at the moment. Strange. Okay. So here's what we said about division. So basically, we have to multiply the numerator and the denominator by the complex conjugate of a denominator to remove the imaginary part of a denominator so we can simplify it. So say here, using the AB example from the previous slides, so I've got 2 plus J3 minus, divide by 5 minus J to the 4. I'm jumping ahead of myself there. So you've got this, so you've got 2 plus J to the 3, and you multiply that now by the complex conjugate of this, which is 5 minus J to the 4. So that will be a plus when you put the complex conjugate in. So it's 2 plus J to the 3 by 5 plus J to the 4 divided by 5 minus J to the 4 times 5 plus J to the 4. So with the bottom, we just square each of our terms. We have 5 squared, which gives us 25, and 4 squared, which gives us 16. So you see here we have a real number on the denominator now. We just multiply this out like we did in previous slides. So we have 10 plus J to the 8 plus J to the 15 plus J squared of 12, which when we combine all our terms and put in our minus 1 for the squared complex number, we end up with minus 2 plus J of 23 divided by 41. So you divide the 41 by each of the terms as such. So our final answer would be minus 0.049 plus J of 0.561. Okay, so that would give you the answer. So essentially just running through it again, take whatever your number is, do the complex conjugate to the bottom and multiply by the numerator and the denominator as we've done here. With the denominator, because you're multiplying a complex number by its complex conjugate, you just square each term to get a real number. You do the multiplication on the top, collect your like terms, divide the real and the complex part by the real denominator value to give you your final answer. Might seem a bit tricky, but with practice, you'll have no problem with it. And there's another example which you can have a look at in your own time. I'm not going to particularly go through that. And again, there's another exercise where you can have a look at it. It's dividing the complex numbers. Okay, so how do we use these things? Okay, so this is similar to the example that we had last week in that slide. So here we have a real value. So if we go from the tip of this vector here, we go down to here, so it's 0.2, 0.4, 0.5, and down here, so it's minus 0.9, so minus 0.5, minus 0.9. So that's our real number, that's our imaginary number. If we go for our purple dude, then we've got 0.2, 0.4, 0.6, 0.7, which goes up to here, and then 0.2, 0.4. So you've got it like that. And again, that is that's your coordinates. So we've got 0.7 on the real axis, 0.4 on your imaginary axis. So if you wanted to add them together, you could just add the two real parts together to give you 0.2, and add the imaginary parts together, in this case, which will give you minus 0.5. And that's what this red arrow is here. It points to the new coordinate. So you've got 0.2 down by 0.5, so that's where it would be. Also, if you put, so you see this purple dude here, and I've got this dotted green line which represents the same length as this. If you put that on the end of the purple dude, it points to the same point. If you took the purple line, put it on the end of the green, again it would point to the same point. So that is another way of which you can look at it. And then once you have your coordinates, you can use the equations that we mentioned in the last video. So the magnitude is the square root of the real part squared plus the imaginary part squared, which gives you this. So it says it's about 0.539, which is about correct. And the phase angle is 10 to the minus 1 of the imaginary part over the real part, which, as you can see here, gives you an angle of minus 68. So there's 0, there's minus 30, there's minus 60. So yeah, minus 68. So we can do this graphically to check that our mathematics here is correct. Okay, so again, we'll go through this in an example in the tutorial. This has been asked on exams in the past, so it is a useful thing to know, and it will be part of a mandatory question, which is in section A. Yeah, there's the equations I was mentioning. So there's your magnitude, which is the square root of a real part squared plus the imaginary part squared, and your phase, which is 10 to the minus 1 of the imaginary part over the real part. So, and the same principle applies if you had multiple vectors. So we've done examples where we've had 3 vectors. So essentially you just add up all the 3 real components, all the 3 imaginary components, and then just do the magnitude and phase calculation. So it's nothing that tricky. Okay, so again, here's just some more examples where you got the real. So you got the a red vector here, a purple vector here, and essentially you can find the real and the imaginary coordinates. You can add them together, and you can find the phase. So that's just another example for you to have a look at. Okay. This is where it gets interesting now, okay? So this is when we're starting to look at resistance in an AC circuit and how each of the components works. So note here that if you have just a power supply with a resistor in it, then if you plotted this on an oscilloscope like here, then your voltage and your current are in phase because there's no phase shift if you have a purely resistive circuit. We mentioned that in the last video, okay? So there's no phase shift happens, okay? That's shown here. So yeah, so basically voltage appears across it. You just use Ohm's law to find the magnitude. The phase stays the same, frequency stays the same. So yeah, I'm not going to read that out. You can have a look at that yourself. So if you put it from a complex impedance resistive notation, then ZR, remember Z is what our term for impedance, it's equal to a real number, so ZR is just equal to R. So if resistance was equal to 20 ohms, then ZR would equal to 20 plus J of 0. So because there's no complex part, which is equal to 20 to the phase angle of 0. So unless you have a complex part, you don't have a phase angle. It's just 0. So the phase diagram here is you've got the voltage and the current in phase with each other here, where VR is equal to I times ZR. So it's basically just replaced the resistive component with the impedance component using our Ohm's law calculation. Okay, so now let's look at an inductive circuit. So here we have just a power supply and an inductor. So, as you can see here, it's not in phase any longer. So here we have our voltage, and here we have our current. So you can see that the voltage reaches its peak before the current reaches its peak. Okay? So the voltage leads the current by 90 degrees. Or the current lags the voltage by minus 90 degrees. But this goes back to that civil expression which I mentioned in the last video. So the CIVL, C for the capacitance, so we don't ignore that. So the VIL bit, the voltage, occurs before the current in an inductive circuit. Okay, so that's basically what's mentioned here. Here's just some of the mathematics behind it. So when you have a sinusoidal current, so we have a current I, which is equal to IP, which is the peak value sine omega t, flows through inductor. Then remember from our previous equation that we had, we only get a voltage across an inductor when the current is changing. So V is equal to L di by dt. We can substitute our IP sine omega t in for our current, which gives us this term here. The peak's not going to change, so we can take that out to give us an LIP d sine omega t, and obviously when we differentiate sine we get cos, so we get LIP omega cos omega t here. And again, we've got to just rearrange that into this format here. So, and then, as we said in the last video, we want to have everything in terms of sine, so we convert the cos to a sine by adding 90 degrees to it. And that gives you a final answer. So the standard form can be written as Vp is equal to IP omega L. So Vp is equal to IP XL, same in the form of V equals IR, where X is remember X is the reactance, okay? And essentially, if we want to also from a direction, then XL is equal to omega L, which is 2 pi FL. If we turn it into the impedance, ZL, we put a J term in there as well to represent it's a positive complex number, which means that it has a phase of 90 degrees. So this is a really important equation. So XL or ZL is equal to J of 2 pi FL. Okay, remember that equation. You will be using it quite a lot. If we were to plot it on a diagram there, then as I said, we have our voltage, which is always at 0 degree phase, so that would go along the real axis, and if it's the current is 90 degrees behind it, it will point downwards on the phasor diagram, like that. So that's what's going on here, to show that the current is 90 degrees behind the voltage. Okay. There's an exercise 5 where we're looking at a inductance circuit. So have a good look at that and we'll go through that in the lecture. Okay, just the last thing today is capacitance in an AC circuit. So again, as you can see here, we've got a diagram like from an oscilloscope that I plotted in Multisim. So here we have a voltage supply with a capacitor. So as you can see here, the current reaches its peak before the voltage. So in this case, in a more capacitive circuit, the current leads the voltage by 90 degrees. So if we go back to our civil expression, CIV, in a capacitive circuit, the current is ahead of the voltage. So you look at it from that point of view. And it's just justified by this graph as well. So if we do exactly the same thing as we did for the inductor, we know from our topics 6 and 7 that I is equal to C dV by dt. So we can sub in our Vp sine omega t term for our voltage, as we did earlier. The V peak isn't going to change, so we can take that out, and then we can do a differentiation, so sine becomes cos again, like that. Obviously, then we have to convert the cos back into a sine by adding 90 degrees to it. So our final answer from our calculation is Vp omega c sine omega t plus 90. Which can be written in the standard form of IP is equal to Vp omega c. So just have a look at the mathematics. So again, we can look at that from a from an equation perspective, and we can come up with a term for xc or zc as well. So in zc, it's minus j over 2 pi fc, which is mentioned here. So we have minus j over 2 pi fc. So that's what gives us our impedance. And because we've got a minus j, that would be an angle of 90 degrees, minus 90 degrees, because it's pointing downwards, which is why we get this 90-degree term here. If we're to draw it, so again, if we draw this on the phase diagram, our VC would be at 0 degrees as our reference point, so our current would be pointing up at an angle of 90 degrees. Okay, but because this is a minus j term, the actual capacitive component actually points downwards, so that's why XC has or ZC has a phase angle of minus 90 degrees. And then here's an exercise to reinforce the capacitor theory. Okay, that's it for topic number 11. Sorry, number 10 even. I'm jumping the gun here. I'll see you soon for topic 11. So take care, guys. Have a good evening, and I'll see you soon. Bye-bye.